In this video, I will talk about how to find the magnitude of the magnetic field when you have a straight wire. Now here I have a straight wire, this one, and there is a current I flowing in it, and it has a length of uppercase L. Now, when you have a wire of any length L, you can find the magnetic field at here. I'm gonna make this to be the observation location. And this point, it is important to remember that this is perpendicular to the midpoint of the wire. So, if you measure the distance from here to here, you're gonna find L over 2. And the same thing from the other side, of course. So this is if the observation location is perpendicular, when this line crosses the wire, it's at the midpoint. Now, this is the expression. The magnitude of the magnetic field that the current here creates at that location depends on the constant, 10 to minus 7, the length of the wire, the current that is flowing in the wire, and the distance r from the midpoint of the wire to the observation location. So the magnitude of r, this is from here to here. And that's it. Now, a simple application of this. Let's say I have a wire that has a length of 1 meter, and there is a current flowing in it. Let's make it half amperes, and the observation location is 25 centimeters away from the wire, from the midpoint. Now, this expression will give us B of the wire mu naught over 4 pi. This is equal to 10 to minus 7. The length is 1. The current is 1/2. And I'm dividing this with 0.25. And then I have 0.25 squared plus L over 2. L is 1, so over 2 will be 0.5 squared, and then I take the square root of that sum. If we do the calculations, we will find 3.6 times 10 to minus 7 Tesla for the strength of the magnetic field at the observation location. Now, this expression is valid for any straight wire. This is this expression becomes a little bit more simple if our wire becomes infinitely long. Now, can you really make a wire infinitely long? No, you cannot. You can only make a wire like very large. Now, practically, what does that mean? Okay, how do you know when you have a very long wire, and how do you know when the wire is not very long? It is all a matter of comparison. So, and in this case, I'm comparing two distances, two lengths. When you compare the distance of the observation location from the midpoint of the wire to the length of the wire, that's how you know whether the wire is very long or not. So for a very long wire, the distance from the midpoint needs to be much less than the length of the wire. This is what it means practically when we say we have a long wire. The wire is so long that the observation location is very, very close to it compared to the length of the wire. And if this is not true, if this statement is not true, then you have to use the more general expression, the one that I just used, that is true for any straight wire. Now, if in this expression R is much less than that, so I'm gonna do a little bit of work here. This is gonna be for a long wire, and it's gonna be approximately true. Mu naught over 4 pi have L times the current divided by R and the square root. Now, as I said, for a long wire, this distance is much smaller than that. Well, if this is much smaller than that, I can just say it doesn't really affect the sum. It doesn't contribute anything to the sum if this is tiny. So I'm gonna leave the square root of L over 2 squared, but the square root with the square goes away. So I have L, I, R, and then L over 2. This L with this L will cancel out. Mu naught 4 pi, I'm gonna bring the 2 in the numerator, 2I over R. This expression is valid only if you have a very long wire, or in other words, if the distance from the midpoint is much less than the length of the wire. This this will make your life much more simple than using this. If you do have a long wire, you can of course use this expression. Remember, I got this from this expression. There is nothing wrong in doing that. It will just cost you more time. If on the other hand you do not have a long wire and you're not certain if you can treat it as a long wire or not, then just go ahead and use this. This will not give you the wrong the wrong number in any case, so long as it's just straight wire. And this is valid, as I said, only if you have a long wire. Now, an example. Let's say I have a length. Okay, I'm gonna keep this number the same, the current the same. What would be a very long wire? So R needs to be much smaller than that, much smaller than 1 meter. 1 centimeter is certainly much smaller than 1 meter. So, in this case, because R is much less than L, if I want, I can use this. I don't want to though. I know that this statement is true, so I'll go ahead and use the more simple expression for the magnetic field. And this will give me 10 to minus 7, 2 times the current, and then I'm dividing this with 0.01 or 10 to minus 2. Now 2 times 0.5 will just give me 1. So I have 10 to minus 7 divided by 10 to minus 2. So this is equal to 10 to minus 5 Tesla. Now I do want, it is interesting. So as I said, in this case, you have a choice. You can use the expression for the long wire. You can use this more complicated expression that is valid for any straight wire, for any length. Using the approximate one, I got 10 to minus 5 Tesla. If you want, if you're curious, feel free to plug in these numbers here in this expression and see what you get. The number that you get from here should be fairly close to the 10 to minus 5 Tesla, which shows why this is a good approximation if you have a long wire. Now, I do want to point out the only thing that I found here was the magnitude, the strength of the magnetic field at the observation location. I will talk about the directions in a different video.